Hello, this is section 2.5 in Calculus 3. 2.5, the topics are points, lines, and planes in R3. So we'll be looking into how to describe by mathematical language, how to describe using mathematical language points, planes, and lines in a three-dimensional space. We'll be talking about the distance between a plane and a point, or a point and a line, how to describe lines, how to describe planes. This, unfortunately, is a pretty long section, all right? So we'll have 4 segments or 4 parts to the lecture video, and I hope you enjoy. Make sure you understand these because these are some of the most fundamental concepts that without understanding these, you will not be able to do well in the rest of the course, okay? So let's get to it. Okay, so again, 2.5, I guess I should write section 2.5. Points, planes, points, lines, and planes. Oh my, you can add that. Right. So what's the big deal about this? Well, you have lines on the plane, and equations of lines on the plane, whether they have slopes, positive or negative slopes, or zero slope or undefined slope. We are going to do something similar for three-dimensional space, and as you can imagine, adding that one dimensional makes things a little more difficult. Okay, and by the way, I forgot to mention that we will be using this, I believe it's 4 or 5 page handout. So if you have not printed this out, you may want to do that, because I don't want you to have to write down, all of these paragraphs, for instance, by hand. Okay, so here's a brief introduction. All right, for each equation, or let's say for equations of any geometric set S, and I have mentioned this before, but basically a set in any space is a set of points. Pick an arbitrary point, okay? In order to describe, for instance, a line on the plane, you pick an arbitrary point of the set, xy, right? And then you ask yourself, what makes this point so special that it belongs to that set S? Let's say S is a sphere, okay? It's a sphere centered at the origin of radius 5. Okay, is 5, 0 part of the set? In other words, is 5, 0 on the circle of radius 5? Of course it is. Okay, but what makes that 5, 0 so special that it is in that set S? Okay, and there are certain characteristics. In fact, usually one defining characteristic or property that the xy satisfies in order to be an element of that set. Okay, and so then you write down that defining description, which I call the membership criterion or eligibility requirement in order to belong to that set S, which is like an exclusive club, right? So I used this analogy before, but the person XY walks into the reception area of this exclusive club S. The S may be a circle or a line or whatever. And XY says to the receptionist, look, I'd like to join your club. And the receptionist will say, okay, let me see your ID. And they see your XY and says, okay, let me see, check your eligibility. And if, for instance, in this situation with a circle of radius 5, if XY satisfies one particular equation, namely x squared plus y squared is 25, then welcome XY, you are in the club. Please pay your dues. Otherwise, there's no way you can belong to our exclusive club. Your name is incorrect, So that's the language of mathematics. And it helps you understand what's going on with the equations of lines, planes, and other mathematical objects. All right, it also helps you sketch pictures. All right, so here's an example. You know all about lines. Ever since Algebra 1, you have been studying lines on the plane, okay? So let's look at a line L that passes through the given point x naught, y naught, and has the slope. So here's a picture. All right, and so it does go through this point, x naught, y naught. Okay, it's a fixed point. Right? And let's say this line goes through x naught, y naught, and has a slope m. Come on. Let me change my mode to a tablet mode. I think that's a little better. okay? And then you ask a question, what makes all these points, let's pick a point here, okay? So this is a point that happens to be on this line. What makes this line, XY, so special that it belongs to this line, L, okay? There is a requirement, right? What is the requirement that XY has to satisfy in order to be on this line, okay? So here you pick an arbitrary point, because what we would like to say is XY is on this line if and only if it satisfies a certain equation. So in this case, the point XY is on L if and only if the slope between these 2 points is M, right? That's the only requirement actually. So then you write that, what I just said, in the language of mathematics, all right? So what does it mean? The slope, that's M, is equal to what? Delta Y over delta X, otherwise called the rise over the run, and that's Y minus Y naught over X minus X naught, right? And so assuming that X is not equal to X naught, this makes sense. And so this has to be equal to M, right? So maybe I can just skip this thing here. All right, so that's the eligibility requirement. Now, normally we write this in this form, Y minus Y naught is equal to M times X minus X naught, okay? You are familiar with this, right? I hope it is. What is this called? This is called the point slope form of the equation of the line L, all right? So that's where it's given. Now, of course, you have other forms like the slope intercept form, but this is exactly the process we are going to take in order to explore lines and planes in space. So for instance, now let's think of a line, okay? This line is actually in 3-dimensional space. I know you can't see it, but you know, it's the background is 3-dimensional space. And you have to be given a few things. First, let's say this line goes through the point X naught, Y naught, Z naught. Now that's clearly not enough to define this line, because how many lines goes through a particular point? Millions, zillions, actually infinitely many, right? But out of those, there's maybe a distinct, special, unique property that this line L is parallel to, or along the side of, or in the same direction of this vector V. Okay, so that now tells you exactly what this line is, okay? And it looks like something happened to my picture on the screen. Hold on a second. Okay, so this is the picture. Now we would like to define or come up with equations that would describe this line L. Okay, so what do? Right, we do the same thing. We pick a point. Okay, random point X, Y, Z on this L, and then we ask this question. Okay, now we are told that X, Y, Z, that's first and middle and last name of this point, a person, is X, Y, Z, and he or she says he or she belongs to this line L. What makes that name so special that the name XYZ belongs to L? What makes that point so special that it is eligible for the membership of this exclusive club called line L? The answer, well, what do you think? The segment, or I would say vector from X naught, Y naught, Z naught to XYZ has to be, not just has to, it doesn't have to be V itself, but it has to be parallel to V, right? That's exactly what we would like to describe in terms of mathematics. All right, so here's what I'm saying here. Given line L that passes through the point X naught, Y naught, Z naught, and it is parallel to, which means in the same direction of, or the opposite direction of, remember a scalar product, of ABC. So this vector V is the vector ABC. Pick an arbitrary point, we did that. Now the point XYZ is on this line L if and only if IFF, the vector between XYZ and X naught, Y naught, Z naught is a parallel to V. Get that? Okay, so it's really not a hard thing. Now you just have to translate that into language of mathematics. You guys all speak that language, right? You have been speaking that in all your previous calculus classes. So the vector between these 2 points is L minus X naught, sorry, X minus X naught, Y minus Y naught, Z minus Z naught is equal to some multiple of the vector V, which is ABC. So it's AT, BT, and CT, where T is some real number, right? And in fact, T ranges over the entire reals because this line has no ends. All right, so this actually immediately leads us to the standard equations of this line. Now, you had different forms of equations of lines in R2, but here we use what is called the parametric equation, right? Or parametric equations. Let's do this. There are several forms here. I'll give you parametric equations, and then the symmetric equation, that's another form, and then I may give you what is called a vector form of the equation of this line. So anyway, the first one, X minus X naught has to be TA. Y minus Y naught has to be TB. And this is really a system of equations. Z minus Z naught is equal to TC. That's exactly, I'm just copying what I wrote. Okay. Now, this is not exactly what we call the parametric equations. I mean, they sort of are, but typically we write in terms of X, Y, and Z. All right, so here are the first set of, here's the first set of equations called parametric equations of line L. X is X naught plus AT. Y is Y naught plus BT. Z is Z naught plus CT. Okay, now this sort of makes sense because when T is equal to 0, XYZ is basically X naught, Y naught, Z naught, that's right here, right? And when T is equal to 1, it basically goes along the side of V and it goes from here to here as T goes from 0 to 1. And as T continues to go on, of course, this keeps going to a positive infinite in direction and then goes to the negative infinite direction. That will cover, as T ranges over the R, this covers the entire line. So this set of 3 equations is called the parametric equations, the parameter being this point T. Right now, if you solve this, solve for, let's say, solve each for T, and here's what happens. T is equal to, okay, let's solve the first one. Basically, it says X minus X naught over A, and T is also equal to Y minus Y naught over B. Also, Z minus Z naught over C is also equal to the T, right? So if you solve each of these for T, what we call, and you see the symmetry among all of these 3 expressions. So the equation, one equation, which has 2 equality symbol, X minus X naught over A equals Y minus Y naught over B equals Z minus Z naught over C. Okay. This one equation is called the symmetric equation of the line L. Now, we don't use this very often. I think by far we'll be using this more frequently, parametric equations. But again, you know, this is one of those things where you can write, describe one thing in different ways. Now, there is another one, sometimes it's called a vector form. I don't think I should have a hyphen here. Vector form of the equation would say something like this. Basically, x, y, z, I mean, this is really the same as the set of parametric equations, is equal to x naught, y naught, z naught, plus tv, okay, where v is, and maybe I shouldn't write v because I didn't use v, but v is, you know, basically ABC. Now, of course, that is the same as, you know, that, right? So there is no difference here, but this is sometimes called a vector form of the equation of the line. All right, I don't have a lot of space here, but let's say, let's practice this, right? So I want you to write the parametric equations of the line that goes through 1, 3, -2, and parallel to the vector 5, 1, 4. I'm not going to pause this. If you'd like to pause this and try to work this out yourself, you can do that. Okay. And when you think you have the answer, you can come back to it. But I am not going to switch to the new part or the new segment of this video yet, because I have a break a little later. All right. So how do you do this? Okay. It's actually really easy. You can do this vertically like I do. X, Y, Z is equal to, right? And I mean, you know, what I do is I just write down the X, Y, and Z coordinates, 1, 3, -2. That's my starting point. I guess I should say line, ooh, look at that. It should be an eraser. I should be erasing this. And in a moment, I think I will. There you go. Okay, what I meant by that is line through this point parallel to V, all right? So that's when t is equal to 0, and all I have to do is to write 5, 1, 4, and then t like this, okay? That's these parametric equations would describe exactly the line that I want. All right, number 2, moving right along, we go into planes, which are flat two-dimensional objects in R3, okay? So this is cool, okay? I mean, I think it's okay for you to just memorize the formula, and you should memorize the formula, but you should really understand where this is coming from, okay? So you have this plane. I'd like to just express this plane, let's call this plane P. P is an unfortunate choice because P could stand for planes or you know, points. But in this case, P stands for the plane. Now, what do you have to know about this plane in order to describe this? Okay, first, it really helps if you have a point on the plane. So you are given that this point, plane P goes through the point x0, y0, z0. But again, there are many, in fact, infinitely many planes that go through this point x, y, x0, y0, z0. And even if I'm giving you like a line, and let's say I have this plane that goes through x0, y0, z0, and it contains this line L. You realize that does not give you a unique plane, because you can have this plane, or you can have you know, this plane. You can keep turning this around, right? So that doesn't give you a unique plane. What does give you a unique plane is a point and a vector perpendicular to it. Now we call this a vector n because it is called a normal vector. A normal vector, the word normal means all sorts of things in mathematics depending on your context. But in this case, the word normal means perpendicular to the plane. So this vector is called a normal plane. Once you are given a normal vector and a point x0, y0, z0 on the plane, then those will uniquely determine the plane. Now you are ready to write the equation. And by the way, let n be ABC. Okay. All right. So how do you write the equation of this plane? We're going to do the same thing. Okay. This point XYZ is fortunate enough to be eligible to be on the plane. In fact, it is. Okay. So is this and this and this. But the point here is not on the plane. Point here is not on the plane. What makes this point, arbitrary point XYZ, what makes this point XYZ so special? Maybe this point XYZ, this point XYZ, all of these are on the plane P. What makes these points so special that they are eligible? They satisfy the eligibility requirement to be on the plane P. They belong to this, you know, fascinating club called P, the plane. What is that? These guys don't satisfy. They have no business walking into the plane because they don't belong there. Ooh, that's exclusive, isn't it? Okay. Well, XYZ satisfies, and think about all these points. How would you describe all of these points that are on P? There's one characteristic, geometrically speaking, right? You know what that is? Think about this. I'll give you a few seconds. If you pause, I can give you more seconds. All right. So the idea is, think of vectors. Let's use another color here. This vector, there's something about this vector. There's something about this vector. There's something about this vector. Do you notice that? Okay, so the idea is if you pick any random point XYZ on this plane, the vector connecting x naught, y naught, z naught, and x, y, z, so those are the green vectors you see here, they are always perpendicular to the normal vector n, right? That is the defining characteristic of all the points on the plane, right? So x, y, z, should I do this? Yeah. I am going to pick an arbitrary point x, y, z. I did that already, right? And then this point x, y, z is on this plane P if and only if the vector between x, y, z and x naught, y naught, z naught is perpendicular to n. Yes, that is the characteristic that defines x, y, z to be an element of this plane or a point on the plane. Okay, now we can say that in English. You may be able to say that in your native language as well. That's going to be difficult to translate this. But translating that into mathematics will give us the formula for x, y, z that would satisfy all the points on the plane. All right, so what is that? First, the vector from x, y, z, x naught, y naught, z naught, and x, y, z. That's x minus x naught, comma, y minus y naught, comma, z minus z naught, comma. That's the vector, one of the, any of the vectors you see in green. That is perpendicular to A, B, C. Okay, this is what I'd like to say. Now that's and this is, by the way, this is a complete English sentence, so I can even put a period here, because that part here is a verb. You see that upside down T? It says is parallel to. I mean, it's a be verb with an adjective. But anyway, what this is saying is that these two are perpendicular to each other. We have a better way of describing this. What is that? Dot product is equal to 0, period. Wow, okay. Well, the rest is actually easy. What is the dot product? A, x minus x naught, plus b, y minus y naught, that's a naught here, plus c, z minus z naught is equal to 0. That is a beautiful equation, right? And this is a perfectly acceptable expression for the equation of this, as an equation of this line. I say an equation because there are many equations, right? For instance, you can multiply everything here by 2 or 100 or negative 37, and those still would describe the same plane, right? Typically though, I sort of like this one as well, just, you know, because these are constants, right? All of these are constants. So you can do ax plus by plus cz, and then you can just put all of these other things together. Negative ax naught minus by naught minus cz naught can be described as some constant d, okay, is equal to 0. So here, d, if you write the more specific description of d, that's negative ax naught minus by naught minus cz naught. Okay, so you can summarize all the, or you can combine all of the constant terms together and write it as a d. One side should be equal to 0. That is probably the best form of the equation of this particular plane P, or in any general, of any general point plane. All right, so of course the d changes, but notice here, A, B, C, these are coefficients of x, y, and z, and those are exactly the components of our normal vector. So by looking at the equation or an equation of a line, you can always tell what a normal vector is. Just read the coefficients for x, y, and z respectively, and you will have a normal vector. That is awesome, right? Because you can just read off of the equation, right? Again, this is as easy as A, B, C. Wow, all right. So let's do an example. I'd like to give you an example here. Let's see, what can I do? Yeah, let's, here's this is an equation. Okay, so what is the equation? What I mean by that is that this is an equation of the plane. Also, this is an equation of the plane. Either one would be acceptable. I'll take, you know, whichever. This is slightly little nicer if you want me to be in good mood, because this is much easier to grade, right? I mean, all right. So, but anyway, I'm not going to penalize you if you write the correct answer, and both of these would be correct answers. All right, so let me just give you an example, not equation, because I've already written an equation. Here's an example question. Try to find an equation of the plane through 1, -2, 4, and perpendicular, let's not use the word normal here, okay, and perpendicular to a normal vector of 2, 3, 1. Okay, let's go ahead and try to write the equation or an equation, maybe the equation with this form where one side is equal to 0. Okay, try to describe this plane through 1, -2, 4, normal to 2, 3, 1. All right, and when you think you are done, you can come back and look at the second part of this lecture.